Over the grey English Channel in autumn 1941, Spitfires roar beneath heavy clouds as
The autumn of 1941. Over the icy grey waters of the English Channel, a new kind of terror owned the sky. For the pilots of the Royal Air Force, it was a waking nightmare. They were the hunters who had become the hunted, flying the legendary Spitfire, an aircraft that had saved their nation just a year before. But now, it was being systematically torn apart. The cause was a machine that seemed to have been forged in a devil's workshop, the Focke-Wulf 190, in the hands of confident Luftwaffe aces. This radial engine masterpiece was an instrument of sheer dominance. It was faster, it climbed harder, it rolled quicker, and it could dive away from trouble with contemptuous ease. The Spitfire Mark V, the RAF's best, was suddenly, brutally obsolete. For every advantage a British pilot tried to press, the Focke 190 had a devastating answer. Wing Commander Johnny Johnson, one of the greatest aces of the war, watched in horror as his squadrons were decimated. "They drove us back to the coast," he wrote, his words heavy with the desperation of the moment. At the Air Ministry in London, the mood was just as grim. Intelligence reports confirmed what every pilot knew in his bones. This wasn't just a better plane, it was a generational leap. The Luftwaffe, once cautious, now prowled the skies with arrogant impunity, seeking out Spitfires for the slaughter. It seemed the Merlin engine, the very heart of the Spitfire, had reached the absolute limit of its potential. While Germany's new killer had just begun its reign, Britain's finest fighter was facing the end of its line. A crisis graver than anything seen since the Battle of Britain was unfolding. And this time, there seemed to be no answer. How do you fight a monster that you can't catch? How do you win a war when your best weapon is no longer good enough? The answer wouldn't be found in the cockpit, but in the mind of a single, brilliant engineer. To understand how this desperate crisis sparked one of the greatest technological comebacks in history, make sure you're subscribed. And let's dive in. 300 miles north, in a cramped office at the Rolls-Royce Experimental Department at Hucknall, Stanley Hooker attacks the altitude problem with mathematical precision. The Oxford-trained engineer understands that single-stage superchargers hit an insurmountable wall above 0 feet. As air density decreases with altitude, piston engines suffocate. At 0 feet, the air contains only 13, the density of sea level, meaning only 13 the fuel can be burned, yielding only 13 the power. The solution requires forcing more air into each cylinder, but existing supercharger technology has reached its limits. Hooker's breakthrough comes through elegant simplicity. 2 supercharger stages in series. The first impeller compresses incoming air, feeding it to a second impeller for additional compression. Between the stages, an intercooler removes the dangerous heat generated by compression, preventing detonation and maximizing power. The 2-stage, 2-speed supercharger concept multiplies compression ratios rather than merely adding them, where the Merlin 3 achieves 3. Woo. 1 compression, and the Merlin 46 reaches 4. Woo. Hooker's Merlin 61 will deliver 6. Woo. 1 compression ratio. The engineering challenges prove immense. The intercooler requires its own cooling system, completely separate from the engine's glycol circuit. Extra radiators must dissipate the heat generated by 2-stage compression. The supercharger casing grows larger and heavier, demanding structural modifications to every airframe that will carry it. Gear ratios require recalculation. Fuel flow systems need redesign. What begins as an engine modification becomes a complete power plant revolution. By January 1942, prototype testing reveals the magnitude of Hooker's achievement. The Merlin 61 generates 300 additional horsepower at 0 feet, compared to the single-stage Merlin 45 at high altitude. A Spitfire equipped with a 2-stage engine will be 70 miles per hour faster than the current Mark V. The performance increase represents what test pilot Geoffrey Quill describes as a quantum leap over existing fighters. But British aircraft production faces an agonizing bottleneck. The purpose-built Spitfire Mark 8, designed specifically for the Merlin 61, won't enter production until late Edesinde o 900 o Togfir. Fighter Command cannot wait that long, while the Focke-Wulf menace grows stronger. Supermarine solution proves both desperate and brilliant. Take existing Spitfire Mark V Charlie airframes and adapt them to accept the two-stage engine. The result becomes the Spitfire Mark IX, intended as a temporary expedient, but destined to become one of the war's most important fighters. The conversion requires surgical precision. The Merlin 61's increased length demands new engine cowlings longer by several inches to accommodate the intercooler housing. Four-bladed RO propellers replace the three-blade units, handling the increased power output more efficiently. Two thermostatically controlled radiators manage the complex cooling requirements of the two-stage system. Additional fuel capacity compensates for the higher consumption of the more powerful engine. Every modification fights against time, while German air superiority solidifies. At Jagershir, 26 Forward Base, at Autumn Bear, Hauptmann Joseph Priller briefs his pilots on RAF tactics. The German ace, who will eventually claim 68 Spitfire victories, emphasizes the continued superiority of the Focke-Wulf. The Tommy still flies, predictably. He tells his squadron, use your speed and climb advantage. Engage when you choose. Break off when you choose. They cannot follow us in a dive or a climbing turn. Pillar's confidence reflects the entire Jaguar's attitude. In early 1942, the FW-190 has restored German air superiority to the Channel front, unknown to Priller. The first production Spitfire Mark IX began rolling off assembly lines in June 1942. Rolls-Royce mechanics at Hucknall work around the clock converting Mark V Charlie airframes. Their modifications guided by engineering drawings that change daily as new problems emerge. The intercooler placement requires restructuring the entire supercharger assembly. Cooling systems demand complete repling. Engine mounts need reinforcement to handle the additional weight and vibration of the two-stage power plant. Flight Lieutenant Allier of 54 Squadron receives one of the first operational Spitfire Mark IX at RAF Hornage. The New Zealand ace, a Battle of Britain veteran, immediately notices the aircraft's different characteristics. The 4B blade propeller provides smoother power delivery. The engine note changes subtly, the two-stage supercharger creating a distinctive whine under high boost conditions. Most importantly, climb performance improves dramatically above 0 feet, where the second supercharger stage engages automatically. On June 23rd, E-10 Jobai Sijurar, the intelligence war takes an unexpected turn. Oberleutnant Armand Faber of Jagerschwader II, pursuing Spitfires after a combat over DEP, becomes disoriented in cloud cover when he breaks into clear air. The coastline below appears familiar to familiar. Faber has crossed the channel and now flies over South Wales. With fuel running low and no alternative, he lands his pristine Focke-Wulf 1983 at RAF Pembrey, handing the British their first intact example of Germany's superfighter. The captured FW-190 undergoes immediate evaluation at the Royal Aircraft Establishment. British test pilots confirm what combat reports have indicated. The German fighter outperforms the Spitfire. Mark 5 inches nearly every category except sustained turns, speed, acceleration, climb rate, dive performance, roll rate, all favor the Focke-Wulf. The only comfort comes from knowing that British engineering has already answered the challenge, though operational squadrons don't yet know it. Squadron leader Brian Lane of 19 Squadron studies the intelligence summary with professional interest. A veteran of the hardest fighting over France, Lane understands aircraft performance from bitter experience. The captured FW-190 specifications explain the mounting casualties his squadron has suffered. 420mm cannon and 27 9mm machine guns provide devastating firepower. The BMW 801 radial engine, air-cooled and less vulnerable to battle damage than liquid-cooled inline engines. gives German pilots confidence to press attacks that would a Merlin-powered fighter at the Rolls-Royce plant and crew. Workers fitting supercharger assemblies to Merlin's 61 engines represent industrial mobilization at its peak. Many are women drawn into aircraft production by wartime necessity. They understand that their precision work directly impacts pilot survival rates. Each impeller must be balanced to micrometer tolerances. Intercooler passages require perfect sealing to prevent compressed air leakage. Gear trains controlling the two-speed supercharger operation demand. Assembly precision matching. Swiss watchmaking. The first operational squadron to receive Spitfire Mark 9s is 64 Squadron at Hornchurch, beginning conversion in July 1942. Squadron leader Don McDonald briefs his pilots on the new fighter capabilities while emphasizing that external appearance remains virtually identical to the Mark V. Jerry won't know what hit him until it's too late. McDonald explains. The Mark 9 looks like every other Spitfire until you light the afterburners at altitude. Flight Sergeant Cyril Bamberger, a Polish pilot flying with 64 Squadron, appreciates the psychological advantage this creates. German pilots have learned to respect Spitfire agility, but not their speed or climb performance. The Mark 9's external similarity to earlier variants means Luftwaffe fighters will engage expecting inferior performance and discover equality or superiority instead. In aerial combat, surprise often proves more valuable than raw performance. July 28th. E-10 Jobai Sishar, 12 Spitfire, Mark 9 of 64 Squadron launch from Hornchurch for the type's first operational mission. A fighter sweep over Le Havre. Squadron leader McDonald leads the formation across the channel at 0 feet. The altitude where two-stage supercharged Merlin demonstrate their greatest advantage. Each pilot monitors engine parameters carefully, watching for signs of overheating or mechanical stress from the complex power plant over the French coast. Radar plots indicate German fighters climbing to intercept for Focke-Wulf 190 seconds of Jagdgeschwader 2, led by Aberluten and Klaus Matusch. Expect another routine engagement with outclassed RAF fighters. Miatas has claimed 15 Spitfire victories and approaches this combat with professional confidence. His FW-19A-3 carries full ammunition for its 4 cannon and 2 machine guns. The BMW radial engine runs smoothly at maximum continuous power. The initial engagement unfolds conventionally. German fighters attempt to use superior speed and climb rate to dictate combat terms, while Spitfires seek turning fights where British advantages traditionally manifest. But Matosh quickly realizes something has changed. The Spitfires climb with him, matching his rate of ascent above 0 feet. When he attempts to disengage by diving, the British fighters follow more closely than Mark V's ever could. His tactical playbook no longer applies. Flying Officer Johnny Plagas, a Belgian pilot with 64 Squadron, presses his attack on Matosh's wingmen with unprecedented confidence. His Spitfire Mark 9's performance at altitude equals or exceeds that of the Focke-Wulf, eliminating the German fighter's primary tactical advantage. When the FW-190 attempts its standard escape maneuver, a roll and dive to the opposite direction, Plage Merlin, maintaining power where single-stage engines would falter. The combat ends inconclusively, but German pilots return to base troubled by the encounter. Motate reports to his commanding officer that the Spitfires performed differently, more aggressively with better high-altitude capability than previous engagements suggested. Intelligence officers note the report but lack context to understand its significance. The RAF has introduced a quantum leap in fighter performance, with no external indication of the change. 2 days later, on July 30th, E-10 Jobai Sisrar, the revelation becomes undeniable. 9. Focke-Wulf, 190 seconds. Encounter 12 Spitfire Mark. 9 Eins, during a diversionary sweep over Saint-Hain, Omar, the German formation, expecting to dictate engagement terms as usual, finds itself meeting fighters that climb, accelerate, and maneuver at high altitude with unprecedented effectiveness. In the swirling dogfight that follows, 5 FW-190s fall to Spitfire guns, while the RAF loses no aircraft. Hauptmann Joseph Priller, leading the German formation, experiences his first taste of aerial combat, where Focke-Wulfs don't hold clear performance advantages. His attempts to use superior speed and climb rate fail when Spitfires match or exceed his aircraft's capabilities. The psychological shock proves as significant as the tactical one. For nearly a year, FW-190 pilots have engaged RAF fighters with confidence born of superior performance. That confidence evaporates in a single combat. Back at Autumn Bear, German intelligence officers struggle to explain the engagement. External examination of crash. Spitfires reveals no obvious modifications. The fuselage appears identical to previous marks. Wing shapes show no changes. Only close inspection of the engine installation hints at modifications. But German technical intelligence lacks detailed knowledge of Rolls-Royce development programs. The performance increase seems to have materialized from nowhere. At Rolls-Royce Derby, Stanley Hooker monitors combat reports with satisfaction mixed with concern. His two-stage supercharger has delivered the promised performance increase, but mechanical reliability remains questionable. The complex intercooling system creates multiple failure points. Supercharger gear trains operate under tremendous stress. Engine temperatures climb higher than single-stage installations, threatening component longevity. Each combat mission tests the limits of engineering margins. The production challenge intensifies as demand for two-stage Merlin explodes. The Air Ministry wants every operational squadron re-equipped with Mark IX Spitfires as quickly as possible. But the Merlin 61's complexity requires manufacturing techniques and materials beyond existing production capacity. Intercooler cores demand specialized fabrication. Supercharger casings need precision machining. Gear trains require metallurgical expertise previously reserved for specialized applications. August 19th, 1942 brings the ultimate test during Operation Jubilee. The Allied raid on DEP. The Royal Air Force commits over 300 fighters to the operation, including 6 squadrons of Spitfire Mark IXs. Jagdgeschwader 2 and 26 respond with 115 fighters, predominantly Focke-Wulf, 190 seconds. The resulting air battle becomes the largest daylight engagement since the Battle of Britain and the first major combat where two-stage Merlin Spitfires meet concentrated FW-190 opposition. Wing Commander Johnny Johnson leads the Canade Wing Spitfire Mark IXs into the melee over DF Harbor. His tactical assessment proves grimly accurate. The Mark IX restores parity with the Focke-Wulf, but doesn't establish clear superiority. German pilots no longer confident of overwhelming performance advantages fight more cautiously. RAF pilots, emboldened by improved aircraft capabilities, engage more aggressively. The result is brutal attrition for both sides. Flight Lieutenant Sailor Mallon of 74 Squadron Flying, one of the early Mark IX conversions, discovers both the promise and limitations of the new fighter during the DUP combat. His two-stage Merlin provides excellent high-altitude performance, but the engine runs hot under combat conditions. Coolant temperatures climb dangerously during sustained high-power operation. The complex intercooling system proves temperamental under G-forces and rapid throttle movements. Mechanical sophistication creates mechanical vulnerability. Obridge fighter Hans Dortmann of Jagdgeschwader 26 experiences the changing dynamics from the German perspective. His Focke-Wulf 193 no longer dominates Spitfires as completely as previous engagements suggested. The British fighters climb with him to altitude, follow him in dives more closely, and maneuver aggressively in situations where Mark Vs would have been easily outrun. The tactical revolution leaves German pilots psychologically unbalanced and strategically disadvantaged. The DFP air battle's aftermath reveals the strategic significance of the Merlin development program. While German pilots claim 60 in RAF aircraft destroyed, they lose 25 Focke-Wulfs in return. More importantly, Luftwaffe confidence in overwhelming technological superiority evaporates. The period of German air supremacy over the Channel front ends not with dramatic defeat, but with grinding parity that favors the side with greater industrial resources. At Jägerschwader II's headquarters, Headman Adolf Gallen studies combat reports with growing concern. German pilots report that some Spitfires perform dramatically better than others, but external identification remains impossible. The uncertainty forces Luftwaffe fighters to treat every Spitfire as potentially dangerous, eliminating the aggressive tactics that made the FW-190 so effective. Operational flexibility disappears when every engagement becomes a potential trap. The intelligence implications extend beyond tactical considerations. German aircraft development has concentrated on incremental improvements to existing designs rather than revolutionary advances. The Messerschmitt Bf 109 Gustav represents evolution, not revolution. The Focke-Wulf 190D model, still in development, promises better high-altitude performance, but won't reach operational squadrons until late 1943. Britain's two-stage supercharger technology has leapfrogged German development by at least 18 months. At the Reich Air Ministry in Berlin, General Ober-Ernst Udet reviews intelligence summaries with mounting alarm. The Rolls-Royce Merlin's transformation from adequate power plant to world-class engine threatens German air superiority across all theaters. If British engineers can achieve such dramatic performance increases, what other surprises await German forces? The technological war has entered a new phase where engineering innovation matters more than pilot skill or tactical doctrine. Stanley Hooker's team at Rolls-Royce continues refining the two-stage concept through late 1942. The Merlin 63, introduced in autumn, produces 1710 horsepower at 8, 500 feet, and 155 horsepower at 21, 0 feet. Boost pressure increases from 15 pounds per square inch to 18 pounds per square inch, extracting additional power from the fundamental design. Each improvement pushes closer to the 2 horsepower barrier that seemed impossible just 2 years earlier. The manufacturing challenge grows exponentially with each variant. The Merlin 66, optimized for low-altitude performance, requires different supercharger gearing and intercooler specifications. The Merlin 70 series, designed for extreme altitude operations, demands even more complex cooling arrangements. Every variant multiplies production complexity, while combat demands accelerate delivery schedules. British industry transforms itself to meet engineering requirements that push the boundaries of 1,940 seconds technology. Flight Lieutenant Pierre Clustermann of 602 Squadron experiences the Merlin evolution firsthand through the autumn of 1942. His initial Mark IX, converted from a Mark V Charlie, suffers frequent mechanical problems as the complex power plant reveals teething troubles. Intercooler joints leak under high G maneuvering. Supercharger gear trains develop backlash under rapid throttle movements. Engine temperatures climb beyond acceptable limits during prolonged combat. But by winter 1942, production Mark IX demonstrate the engineering maturity that transforms experimental technology into operational reality. Clustermann's replacement aircraft, built specifically for the two-stage Merlin rather than converted from earlier airframes, proves reliable under combat conditions. The intercooling system operates flawlessly. Supercharger engagement transitions smoothly between single-stage and two-stage operation. Power output remains consistent across the altitude envelope. The tactical revolution spreads beyond the Channel front as Spitfire Mark IXs reach operational theaters worldwide. In North Africa, RAF squadrons received their first two-stage fighters in September 1942 against Messid Bf 109, Gustavs operating at the limits of German logistics. The Mark IX's performance advantages proved decisive. High-altitude interceptions previously impossible, with single-stage Merlin become routine operations. Squadron leader Killer Caldwell of 112, squadron operating from landing ground 172 near El Alamein, discovers that the Mark IX transforms desert air combat. The two-stage supercharger maintains power output despite the reduced air density at high altitude, while the intercooler prevents detonation under extreme temperature conditions. German fighters already struggling with fuel and maintenance shortages cannot match the sustained high-altitude performance of properly supplied British aircraft. Major Hans Wim Marseille, the Luftwaffe's leading desert ace, encounters his first Spitfire Mark IX during a combat patrol over L'Alamein in October 1942. The German pilot, accustomed to dominating desert skies with his Messed Bf 109 Gustav, finds himself matched by a Spitfire that climbs with him to altitude and follows him through high-speed maneuvers previously beyond RAF fighter capability. The engagement ends inconclusively, but Marseille reports significant improvements in British fighter performance. The technological race accelerates through late 1942 as both sides seek performance advantages. German engineers work frantically on improved supercharging systems for the Daimler-Benz DB 605 engine. But their single-stage approach cannot match the dramatic gains achieved by Stanley Hooker's two-stage concept. Focke-Wulf develops the TA-152 ultra-high-altitude interceptor, but the complex aircraft won't reach production until 1944, too late to affect the crucial period when Allied bomber offensive reaches full intensity. At Wright Field in Ohio, American engineers study detailed drawings of the Merlin 61 provided under Lend-Lease agreements. The Packard Motor Company receives production licenses for the two-stage Merlin, designated V-1653 in American service. The engine will transform the North American P-51 Mustang from a good low-altitude fighter into the war's premier long-range escort capable of accompanying bomber formations to Berlin and back. The technological transfer multiplies Allied advantages while German development stagnates. By December 1942, the strategic implications of the Merlin Revolution become clear. German air superiority achieved through tactical innovation and aircraft design excellence crumbles before British engineering sophistication and industrial capacity. The Luftwaffe faces the same dilemma that confronted the RAF in early 1942. Their best fighters have become inadequate overnight, while replacement aircraft remain months or years from operational service. The production statistics tell the story of industrial transformation. In 1941, Rolls-Royce produced approximately 8 Merlin engines, predominantly single-stage variants. By 1943, annual production exceeds 000 engines. With two-stage variants comprising 60% of output, American Packard production adds another 000 engines annually, creating a combined Allied output that dwarfs German engine manufacturing capacity. Squadron leader, Alan Deer, now commanding 332 Norwegian Squadron, equipped with Spitfire Mark IXs, reflects on the transformation of aerial combat during the winter of 1942 to 1943. The Mark IX changed everything. He records in his logbook, Jerry could no longer dictate the terms of engagement. We could climb with him, dive with him, fight him at altitude where single-stage engines gasped for air. The hunter became the hunted. The psychological impact on Luftwaffe morale proves as significant as the tactical consequences. German fighter pilots accustomed to technological superiority since the Spanish Civil War find themselves flying aircraft that no longer guarantee survival. The Focke-Wulf 190 remains formidable, but formidable no longer means dominant. Pilot confidence erodes as mechanical advantage disappears, creating a downward spiral that no amount of tactical skill can reverse. At the Meshmid Design Bureau in Augsburg, Chief Engineer Willie Messed studies intelligence reports on the improved Spitfire performance with professional admiration and strategic concern. The British achievement represents exactly the kind of engineering breakthrough that German designers have sought without success. Two-stage supercharging offers dramatic performance improvements without fundamental airframe changes, extending the operational life of existing aircraft designs indefinitely. The broader implications extend beyond fighter combat. Two-stage supercharged Merlin's power. The de Havilland Mosquito high-altitude bomber making RAF reconnaissance and precision strike missions possible at altitudes where German interceptors cannot reach. The Avero Lancaster heavy bomber receives Merlin variants optimized for high-altitude operations. improving bombing accuracy while reducing losses to fighter attack. Engine technology transforms every aircraft type it touches. In the research laboratories at the Royal Aircraft Establishment, engineers analyze combat data to refine two-stage supercharger performance. Further, each engagement provides information on optimal altitude settings, boost pressure limits, and cooling requirements under combat conditions. The feedback loop between operational experience and engineering development accelerates improvements at a pace German development cannot match. The climactic moment arrives in February 1943, when the first Spitfire Mark IX equipped with the Merlin 66 engine demonstrates the ultimate potential of two-stage supercharging. At 21.0 feet, the new variant achieves performance 30 miles per hour superior to the Focke-Wulf 95. Below 27.0 feet, no German fighter can match its combination of speed, climb rate, and maneuverability. The technological revolution reaches maturity. Wing Commander Johnny Johnson, flying the new variant over France, experiences the culmination of 2 years of engineering development. His Spitfire Mark IXB accelerates past diving Focke-Wulfs, outclimbers Bf 109 Gustavs, and maneuvers at altitude where earlier fighters would have stalled. The sensation resembles flying a completely different aircraft, despite external appearances remaining unchanged. British engineering has achieved what seemed impossible in early 1942. German response comes too late and too limited. The Focke-Wulf 190D9, entering service in autumn 1943, incorporates liquid cooling and improved high-altitude performance. But production numbers remain inadequate to challenge Allied air superiority. The Messerschmitt Bf 109K4 offers better performance than earlier variants, but still cannot match two-stage Merlin capabilities at altitude. Technological innovation requires industrial capacity to become strategically decisive. The final accounting reveals the magnitude of Stanley Hooker's achievement. From the prototype's 700 horsepower in 1933 to over 2,000 horsepower in specialized applications by 1945, the Rolls-Royce Merlin's development represents one of engineering's greatest success stories. The two-stage supercharger alone added 300 horsepower at 30.0 feet, transforming adequate fighters into world beaters and creating the foundation for Allied air supremacy. By war's end, over 165,000 Merlin engines power Allied aircraft across every combat theater. The engine that began as a private venture becomes the most successful aircraft power plant in history, defining air warfare for a generation. But its greatest achievement remains the desperate 18 months of development that answered the Focke-Wulf challenge and restored the balance of aerial combat when Britain needed it most. The strategic implications echo through military history. Technological superiority once achieved proves temporary unless sustained by continuous innovation and industrial investment. The Luftwaffe's dominance lasted less than a year before British engineering excellence and production capacity restored parity and ultimately established superiority. The lesson resonates across every subsequent technological competition. Engineering sophistication supported by industrial might determines the outcome of modern warfare more decisively than tactical brilliance or individual courage. In the end, Germany's shock at Britain's Merlin engine evolution reflected more than surprise at specific performance improvements. It represented the moment when German technological confidence confronted Allied industrial determination, when Luftwaffe tactical superiority met RAF engineering excellence, when the limits of incremental development crashed against revolutionary innovation. The two-stage supercharger didn't just add horsepower, it transformed the fundamental mathematics of aerial combat, creating advantages that no amount of pilot skill could overcome. The Rolls-Royce Merlin's journey from 1,000 to 2,000 horsepower stands as testimony to human ingenuity under pressure, industrial capacity mobilized for survival, and engineering vision that changed the course of history. Stanley Hooker's intercooled two-stage supercharger may have been measured in pounds of boost pressure and compression ratios, but its true measurement lay in the stunned silence of German pilots who discovered their technological superiority had vanished overnight. replaced by parity that would inevitably become inferiority as Allied production outstripped German industrial capacity. And so, the revolution was complete. The hunters had indeed become the hunted. In the skies over occupied Europe, the distinctive, high-pitched whine of a two-stage supercharged Merlin engine became the sound of parity, then of superiority, and finally, of dominance. It was the sound of a technical crisis being met with sheer engineering genius. The stunned silence of the Luftwaffe's aces in their cockpits was the true measure of Stanley Hooker's achievement, a victory won, not with bullets, but with slide rules, blueprints, and the relentless pursuit of power. The Merlin 61 and its descendants did more than just save the Spitfire. They became the heart of the Allied air armada. That same roar of innovation that first echoed in a Derby test stand would soon power the P-51 Mustangs all the way to Berlin and back, shattering the Luftwaffe's ability to defend its homeland. It would lift the Lancaster bombers high into the stratosphere, beyond the easy reach of enemy flak and fighters. From a position of near-desperate defense, British engineering had delivered the engine that would power the final, crushing offensive. The story of the two-stage Merlin is a powerful reminder that in the crucible of conflict, technological supremacy is never permanent. It is a fleeting advantage, destined to be challenged and overcome. It was a lesson the Luftwaffe learned at a terrible cost, and a testament to the quiet, determined engineers who, facing their nation's darkest hour, answered the challenge and, in doing so, changed the course of the Second World War. What do you think was the most critical technological turning point of the war? Let us know your thoughts in the comments below. And if you found this story of engineering and aerial combat compelling, be sure to hit the like button and subscribe for more chapters from history. Thanks for watching.